In the previous video, we have studied how we can find the eigenvectors, okay, corresponding eigenvalues. So, in this video, we are going to learn some of the properties of eigenvectors. The first property says eigenvectors are not unique. Okay. Second one is x1 xt, that is transpose, is equal to 0. If this condition satisfies, then x1 and x2 are called orthogonal to each other. Orthogonal to each other. What does it mean? Suppose you find the value of x1. Suppose you have lambda. Let me take an example. Suppose you have lambda is equal to -1, okay, and you got the eigenfactor x1 from that lambda value. You know how to do it. Suppose you have another lambda value, lambda 2, which is -6. You get x2 for this eigenvalue, that is x2 is the eigenfactor corresponding to this eigenvalue -6. Now what you do? Suppose you get x1 as 1 2 3 and x2 as suppose 4 1 3. What you need to do, you have to take transpose of this one, which is equal to, the row will become column. Now if you take x1 x2 t, and if you get 0, then they are orthogonal to each other. If they are not, they are not orthogonal to each other. Sometimes there might be a question that you have to check the orthogonality. This comes in your graduation though, not in competitive, but the condition might be asked, so this is the condition. Okay, just you have to do the product, and if you find 0, they are orthogonal. If they are not, they are not orthogonal. This is the simple funda. Okay. So next, eigenvectors of a symmetric matrix corresponding to different eigenvalues are orthogonal. Okay, this is very important. Number 3, let me write. Okay, so eigenvectors of a symmetric matrix corresponding to different eigenvalues are orthogonal. Suppose there is any symmetric matrix, and suppose a 3D matrix, and you people get 3 eigenvalues from that, and then this condition will get satisfied. Was that? For 3D it is this one, this will equalize this to 0. You can also take this transpose, no issues. And for 2D, both are correct. Okay, we'll solve a problem. This is the condition of orthogonality. And there is something called normalized form of a given Coulomb matrix, and the normalized form, I am writing NF. This is normalized form, is given by root over a, like this. Okay, This you will get application in quantum mechanics, not in mathematical physics much. So these are the basics. Kindly remember. Okay. Now let us read something called algebraic multiplicity and geometric multiplicity. Algebraic multiplicity is what? Suppose you solve, there is a matrix given and you get corresponding eigenvalues from that matrix. Suppose you get from a 3D matrix you get lambda 1 as 1, lambda 2 as 1, and lambda 3 as 2. So the number of eigenvalues repeated, that is degenerate eigenvalues, here is 1, and lambda 3, that is non-degenerated, only one value is there, which is 2 here. So what we say, the algebraic multiplicity of this matrix, I repeat, algebraic multiplicity of this matrix is AM. I am writing algebraic multiplicity for what we write, algebraic multiplicity we write in this way, multi, this is multi, this is A at the base, algebraic multiplicity for 1 for this eigenvalue is equal to 2, that is it is 2 times repeated, times repeated. Okay. Okay, what is the algebraic multiplicity of 2 here? That is this 2, how many times it is repeated? 1 time, so it is 1. Do you get my point? Let's do another example. Suppose there is a matrix and you get the eigenvalues as 2, 3 and 4. What is the algebraic multiplicity of 2 here? 1. That is how many times an eigenvalue got repeated, or what is the number of eigenvalues. If there are 2 eigenvalues which is 3, then the algebraic multiplicity will obviously of 3 will be 2. Okay, suppose there is lambda 2, suppose there is lambda 2, there is lambda 2, we get the same eigenvalues. What is the algebraic multiplicity of this one of 2? 3. This 2 is repeated 3 times. Okay, again, suppose this matrix is given 3, 4, 5, 0, 0, 0, 3, 2. What are the eigenvalues of this upper triangular matrix? I told you it is lambda 1 is equal to 2, lambda 2 equals to 3, lambda 3 is equals to 2. Okay, so how many times, what is the algebraic multiplicity of 2? How many times it is repeated? 2 times, so it is 2. How many 2's are there? How many 1? How many 3 is there? 1. Algebraic multiplicity of 3 is 1. Algebraic multiplicity of 2 is 2. Simple. Okay, let's come to geometric multiplicity. Multiplicity. Okay, so suppose we have any matrix and we get the eigenvalues from there is minus 3, lambda 2 is minus 3, and lambda 3 is 5. We know that eigenvectors are never unique. because based on the ratio we are having, if we are having the same eigenvalue, we will have different eigenvectors for these eigenvalues, because it solely depends on the ratio. We can multiply any number in any ratio, right? So what is the algebraic multiplicity of minus 3 here? How many times minus 3 are there? 2 times. Okay. How many times 5 is there? 1 time. So the algebraic multiplicity of 5 is 1. So from this minus 3 we can get 2 eigenvectors. So what is geometric multiplicity? The number of eigenvectors we get from a single eigenvalue. Suppose, suppose, this is just example. This portion is not so important I am teaching, but short question may come. Suppose we have lambda is equal to minus 3. Okay, for this eigenvalue we can get, suppose we get two eigenvectors. One is 0, 3, 2. These are just examples. Okay, I'm not solving anything. And 3, 0, 1. We may get more, but as this is, there are 2 here, 2 minus 3, so we will get 0, 3, 2, but we can organize them in any fashion. Leave it. So what will be the geometric multiplicity? Geometric multiplicity of minus 3. There are two eigenvectors corresponding to this minus 3, so geometric multiplicity will be 2. What is the geometric multiplicity of minus 5 here? It is 1. See, we will get only one eigenvalue. There is one property. If the geometric multiplicity corresponding to a lambda equalizes the algebraic multiplicity, then this lambda is known as, it's called regular eigen value. Okay, so I think this concept is clear to you. Algebraic and geometric multiplicity, they are not so important, but I have covered it. Hope you understand. Thanks for watching the video.